According to kinetic molecular theory, we learned that gas particles do not have any attraction or repulsion between them. That is why it takes the whole or entire space in the container, right? Whereas in the case of solids and liquids, it has definite volume because there is an temporary attraction between the molecules. Here the dotted line is that temporary attraction and which is weaker, and we call that one as intermolecular force of attraction or IMF in short. So the atoms in this HCl molecule is held together by a strong covalent bond which is represented by a solid line that is within the molecule. Whereas the dotted line here, the IMF is weaker and that is between the molecule. So when it breaks, we can get that molecule separate and it can be in the gaseous form. So we are going to discuss more about IMF in this video. Okay, so don't get confused with the words intermolecular and intramolecular. Intermolecular is the between the molecule and intramolecular is within the molecule. So that is covalent bond, ionic bond, metallic bond, etc. are intramolecular, that is within the molecule. And we are going to focus more on the between the molecule attraction, which is IMF. The strength and type of intermolecular forces can explain the trends in melting point and boiling point and even solubilities, and it can explain many of the unique properties of water. We will discuss 4 types of IMF: dipole-dipole, hydrogen bonding, London dispersion forces, or in short LDF, and ion dipole in this video. Dipole-dipole interaction occurs in polar molecules. If there is permanent dipole, and there will be dipole-dipole attraction. So how will you decide whether the molecule is going to be polar or non-polar is based on the electronegativity difference between the atoms as well as the shape of the molecule. So if there is an uneven distribution of electron density, that molecule is going to be polar. So for example, HCl, in this case, chlorine is more electronegative, so the shared pair of electron will move towards chlorine atom, and the chlorine atom will have slight negative charge and hydrogen will have slight positive charge. So the negative part of HCl will attract it to the positive part of another molecule of HCl. That creates dipole-dipole attraction. Now consider another example, CCl4. We can draw the shape of CCl4 as tetrahedral as shown here. And we can see that there is a slight positive charge on carbon and slight negative charge on each chlorine because chlorine is more electronegative. In this molecule, we can see that these bonds are polar, whereas the whole molecule will be non-polar because there is no uneven distribution of electron density because the dipole moment cancel each other. So there will not be any net dipole moment in this molecule. So we will not have dipole-dipole interaction in this case. No net dipole. Whereas if you remove one of the chlorine by hydrogen, so that means if it is chlorine here, and one of the chlorine is replaced by hydrogen, we will have a net dipole in this case because we don't have a dipole moment that cancels for this one, right? So we will have a net dipole in this case, and this molecule is going to be polar, and there will be dipole-dipole interaction in this molecule. Now look at these examples here. We can see different molecules with a similar molecular weight. Only difference is one of the atom is replaced by a highly electronegative element. In this case, we can see oxygen, one oxygen, and in this case, again one oxygen, but in this case, nitrogen, and there are no oxygen in this case, only carbon and hydrogen. So that makes a difference in the polarity. So the dipole moment in this case is 0.1 dB, in this case 1.3, 2.7, and 3.9. So what happens here is the polarity increases. When the polarity increases, the dipole-dipole attraction increases. When the dipole-dipole attraction increases, that means that gives a stronger IMF. So that stronger IMF results in higher boiling point. So that's how we can explain the properties based on the IMF. Now, hydrogen bonding is a special type of dipole-dipole interaction. When hydrogen bonded with nitrogen, oxygen, or fluorine, we call that one as hydrogen bonds. So the hydrogen should be in between one of those three elements. It can be the same elements or combination of two of these. So it should be, the hydrogen should be in between oxygen and oxygen here, or fluorine and fluorine here, and nitrogen or nitrogen. Now you can see the combination of two of these, that is nitrogen and oxygen, and here oxygen and nitrogen. It can be any of these combinations. So it should be, the hydrogen should be sandwiched between these three elements, and then we call that special type of dipole as hydrogen bonding, which is stronger among these all intermolecular force of attraction. Now let us try to draw the hydrogen bond between HF molecules. Let us take 5 of them and see how to draw the hydrogen bond. So hydrogen covalently bonded with the fluorine. So fluorine is more electronegative, so the shared pair of electron will move towards fluorine, so it will get a slight negative charge on this side and positive charge on hydrogen. So this is polar, and since it contains hydrogen and fluorine, we can see that it can form a hydrogen bond with the neighboring HF molecule, which will have positive charge on hydrogen and negative charge on fluorine, and it will continue like that with another molecule. And 1, 2, 3, and now we can draw 2 more. We can draw any number as we want, but I'm just showing 5 HF molecule. How is it forming hydrogen bond? How can we represent that one through hydrogen bond? So 1, 2, 3, 4, 5 molecules. Okay, so this is how we can show the hydrogen bond. So we can see that it is, hydrogen is sandwiched between fluorine and fluorine. Hydrogen is in between fluorine and fluorine. In odd cases, we can say that fluorine and fluorine. Okay. Another example is water molecule, because water also contains oxygen and hydrogen. So water molecule we will draw like this. These solid lines are the covalent bond, and oxygen is more electronegative, so the electron pair will be pulled towards oxygen, making water molecule slightly negative on oxygen and slightly positive on hydrogen. So this oxygen can bond, hydrogen bond with the hydrogen of another water molecule. Positive and negative attract. You can see this hydrogen is sandwiched between two oxygen here. And we can draw more molecules. This hydrogen can go with oxygen. So we can continue drawing the hydrogen bond among water molecules. Here we can see the representation of adenine and thymine from DNA molecule, adenine and thymine, and you can see that that is attracted through hydrogen bonding. The molecules are attracted through hydrogen bonding. So we have to see which one is the correct representation of hydrogen bonding here. So what I will do, I will check with the bond formation of hydrogen with the phone elements. That means fluorine, oxygen, nitrogen. So on both sides of hydrogen, I will look for these elements. So then in the first case, I can see hydrogen, the dotted line is here. So that is between nitrogen and carbon. So it's not phone element on both sides. So I will not go with that. In the second case, hydrogen is bonded to nitrogen and carbon here. So I cannot go with that because I don't have carbon in this list. So then here hydrogen, again hydrogen here and nitrogen. So I cannot pick that answer either. And in the last case, hydrogen on both sides, I can see four elements. So that is nitrogen and oxygen. So that is the correct representation of the hydrogen bond in DNA molecule of adenine and thymine bases. And now this graph shows the boiling point of some hydrides from different groups. Say for example, group 14, we have carbon, silicon, germanium, and tin. We can see that in the graph carbon, silicon, germanium, and tin. This hydride shows that the boiling point increases gradually, right? From carbon through tin. That means when you go down in the group, the boiling point increases. Whereas in the case of 15th group, we can see that nitrogen, the hydride of nitrogen, that is ammonia, got very high boiling point, and then it is going down. For hydride of phosphorus, the boiling point is very low compared to NH3, and then it is gradually increasing. And now in the case of 16th group, similar trend we can see. 16th group is oxygen. So for water, it is very high boiling point, and then it is going down when it goes to sulfur. Very low. Boiling point is very low compared to water here. Here the boiling point is very high. And then it is gradually increasing when it is going down in the group. Similar trend again for the 17th group. We can see for the boiling point of HF is very high. And then it is going down for chlorine compared to HF. And then it is gradually increasing. What is the reason for that one? When you look at the molecule, you can see water contains oxygen, and HF contains fluorine, and NH3 contains nitrogen. All these three, we know the four elements can form hydrogen bond. So the hydrogen bond is strong. So the IMF is going to be stronger for these three molecules compared to the other hydrides in that group, and therefore the boiling point is going to be higher for those molecules.